Hello everyone, in this video we are going to solve the question coin change permutations. Now this question is just a slight variation of target sum subset and coin change combinations. So if you haven't checked those videos out before, those problems out before, I highly recommend that you do, as this question is really just slightly different from coin change combinations especially. So the link to the other two problems would be in the description box below. Please check them out first, right? It would give you a great insight of this question as well. Moving on to the question that we have for now in our hand, which is coin change permutations. If we look at the objective of the question, which is over here, and read it out to understand what the question asks from us, we would see that it says that you are given a number n representing the count of coins, right? So you would be given coins and they would be having certain denominations each. And then you would be also given a number AMT, which is amount, right? And you are required, if we read this line, which is very important, you are required to calculate and print the number of permutations of the n coins using which amount AMT can be paid, right? You have to pick coins from the set of coins that would be provided such that the summation of that set is equivalent to the given amount. All right, I hope it's a bit clear by now because we have done similar question which is coin change combinations, right? So the only difference from coin change combination is that in this question we are interested in permutations as well, so we want rearrangements. If you look at the notes that we are provided with, we can read them out, and they say that you have an infinite supply of each coin. That is, the same coin can be used for many installments, right? So if you have coins like 2, 3, 5, and 6, you can use 2 multiple number of times, right? You can use 2, 2, and 2 to pay 6. This is what it means. We have infinite supply for each coin, right? The second note that we have over here, it says that you are required to find the count of permutations and not combinations. That means 223, 232, and 322 are the different permutations of the same combination, right? So what does this mean, right? To understand this a bit better, let's take a sample input test case. Okay, so let's suppose for input, what I have is coins which range from 2, 3, 5, and 6. Let's suppose I have these 4 denominations available with me. And for amount, which is AMT, let's suppose I have been given 7, right? To make 7, let's see what we can do. So if I take 2, I can have 2 with 5, right? The summation of this would give me 7, right? But as we are also interested in permutations of each set, what we can do is we can rearrange this. We can rearrange 2, 5 to generate permutations. So if we rearrange, we would get 5 and 2. Right? There is only a single rearrangement that's possible. Again, if we go back, we can see that we can maybe use 2 twice and then 3 for a single time. This would also result in 7 as a summation, right? Again, if we rearrange this, we would get something like 2, 3, 2, or maybe 3, 2, and 2, right? So we were able to rearrange this 2 times. This brings us the answer. This is the total number of valid permutations that have a summation equivalent to 7, right? So these are a total of 1, 2, 3, 4, 5. So we have a total of 5 permutations, right? Now, if this was the previous question, which was coin change combinations, then we would have been just interested in the combination, particular combination. So in that case, our answer would be just these 2, right? But in this case, as we are rearranging, because we want permutations, we get these 3 other rearrangements in addition to the combination. That makes it 2 plus 3, which gives us our answer, which is 5, right? I hope it's clear, and I hope how it's different from the previous question that we have solved, right? So like every other DP question, I would like you to try this out on your own, and if you get stuck somewhere, take the help from article or maybe watch this video again, right? So let's discuss the solution now. So for every DP question, what we do is 3 steps. So the very first step, which is assigning the storage and meaning. So we assign storage and meaning to those storage, right? Each and every position in the storage should have a meaning, right? Second, we derive the direction in which you want to move, right? And the third and the last step is to traverse and solve. We traverse and solve in the direction towards our answer. All right. So in this question, for the very first step, which is assigning the storage, what I would do is I would assign a storage of a 1D integer type array of size amount plus 1. Right. Let's see. I said I would assign a storage, a 1D storage, which is this, and I said that it would be having size amount plus 1. That means the indices would go from 0 to amount, right? Let's take a sample input case of similar to what we did. We have I take the pin. Let's suppose I have 2, 3, 5 and 6. These are my coins, and let's suppose 7 is my amount, right? So if 7 is my amount, I will have indexes from 0 to 7. So let's write them down. 1, 2, 3, 4, 5, 6 and 7 over here, right? Now what I would do is create separations. Okay, we'll take line, create separation over here, right? 2, 3, 4, 5. This one is for 5, this one is for 6, and last one is for 7. All right. So now that we have assigned storage of size amount plus 1, let's write this over here. The size is amount plus 1, right? What does each of these position mean? What does this mean, right? This is my DP. What does DP of 4 mean, right? So I would say that DP of 4 means the number of permutations that I can make using the set of coins that are provided with me, such that I can make a summation of 4. Again, what would DP of 2 mean? DP of 2 would mean using the coins that I have, which are 2, 3, 5 and 6, all of the coins. What are the total number of permutations I can create such that the summation of those permutations is equivalent to 2, right? Okay, so let's generalize this, right? So if this is my DP, then I would say that my DP of I means that number of permutation using all the coins such that amount is equal to I. Whatever index I'm currently in, that would be my amount, right? So if you think about it, what would DP of 0 mean? What is the possible number of ways to generate a summation of 0? We can only generate a sum of 0 if we don't do anything, if we don't take any coin, right? So there is just one way of generating a summation of 0, which is not taking anything, right? Not taking any coin would give me a summation of 0. I don't have to pay anything. Not pay anything, to pay an amount of 0, there is only one possibility, that I don't pay anything, right? So this would be my base case. This would be my base case. DP of 0 is equal to 1 is my base case. So if I write over here, so DP of 0 equals to 1, this would be my base case, right? Now, if we think about it, what would be this part, DP of 7? DP of 7 is nothing but DP of 7 is nothing but DP of amount, right? DP of amount. What would DP of amount mean, right? By the definition that we have over here, DP of amount would mean number of permutations such that amount is equivalent to amount, right? So the initial amount that we had, what are the total number of permutations such that I can make that amount? This is my answer. Makes sense, right? So we derived that this point would store my answer. All right. Okay. Now, what we know is that on DP of 0, we would have our base case. DP of 7, we would have our answer. That means, of course, we would be moving from left side to right side, which is in forward direction, right? So we have discussed the first 2 points, which are assigning storage and meaning, and the direction in which we have to solve, which are similar to what we did in coin change combinations, right? The only part different from coin change combinations is the third part in this question, which is traversing and solving. So let's see how it's different, right? Let's quickly traverse and solve over this, right? So again, what we are going to use is the similar approach of source to destination, right? If I erase all of this, which we wrote for understanding, right? If we come back to our DP and if we see at position 1, which means my amount is now equivalent to 1, what are the possible ways I can reach 0 from 1, right? So what I have is my source as 1 as my destination as 0, right? What are the possible ways in which I can reach 0 from 1? I can only reach 0 from 1 if I have a coin which has value smaller than equal to 1. In this case, my coins array has value starting from 2, right? We don't have any value which is smaller than equal to 1. So I cannot ever reach 0 from 1. I cannot make a summation of 1 from the given set of coins, right? So the number of permutations would remain 0 in this case. Now if we move forward to position 2, right? What does position 2 say? If my source is 2, what are the possible ways for me to reach my destination, right? What I can do is I have intermediates. I can call for 2. As I have my coin as 2, I can call for 2. 2 would get me to 0, right? And 0 would say, okay, there is only one way from me till 0, which is not doing anything, right? So it would return 1 over here, right? Again, let's see this again. What I need to do is I need to get to 0. Currently, I'm at 2. From 2, what are the calls I can make? If I look at this array, if I traverse, the very first number that I encounter, the very first coin that I encounter is 2. Can I make a call of 2? Yes, I can. As the amount is equivalent to the value of the coin, I can make a call of 2. So if I make a call of 2, 2 minus 2 will get me to 0, right? Now 0, if we see over here, has 1. What does this 1 symbolize? It says that there is only one permutation to reach 0, right? Which is not doing anything. So 0 would say that to reach 0, there is only one permutation. So 2 would get 1 as an answer, right? Now I would move forward in my coins array. I would go to 3 and see if the given coin, which is of 3, is of value which is smaller than equal to the amount that we have, right? So 3 is not smaller than 2. That means we cannot call for 3. We cannot call for 5. We cannot call for 6. Right? So as we cannot call for any of these, the only call that I was able to make was for 2, which gave me 1 as the output. So I get 1 over here, right? If we see this on the DP, if we see the similar thing on DB, what we did was from 2, I called for 2 back and got the answer, right? So from 2, right, from 2, which was my DP of I, which is my current amount, I jumped back to my coin's value. So the whatever the coin that I had, I jumped back to that amount. And what I did at the end was had that add up. So this is the formula that I'm working with, right? At the current point, I am getting all the permutations that I got from mediator, okay, which was 0 in this case. Okay, let's move forward and it would be much more clear in that. Okay, so now we are in position 3, right? So our source is 3, our destination is 0. From 3, I can make 2 calls, from 2 and from 3. If I make a call for 2, I would get to 1. 1 would say that there are 0 possible ways from me till 0, right? 1 would say there are 0 possible ways from me till 0. Then what I can do is 3, call for 3, I would reach 0, and 0 would say, okay, there is one possible way from me to 0. 3 would add all the possible ways, which is 0 plus 1, and give me 1, right? So if we see this on the DP, what's happening is the very first coin that I got is 2. So I went from 3 minus 2, which is 1, and 1 said, okay, there is 0. So I did 0 plus. Then I called for another coin which is possible, which is 3. So 3 minus 3 got me to 0. 0 said there is one possible way, and I added 1. This gave me a total of 1, right? So if we see We got a total of 1 over here. And how did we get that one? From 2, I just went to 2. Right? From 3, I just went till 3. Right? Just a single call. Right? If we move forward in our array again, if we come at 4, now I erase this, my source becomes 4, my destination is still 0. I can call for 2, or I can call for 3. If I call for 2, I would reach 2. Right? I would call for 2 and I would reach 2. 2 would say there is one way. 2 would say there is one way. That is, if you attach 2 behind my all the permutations that I have. Right? So what I would get is 0.22. Right? There is just one way. If I call for 3, that would land me up on 1. 1 would say there is 0 possible ways, right? So 4 would do 1 plus 0, which would give me 1, right? So if we see over here, we have just one permutation of making 4, right? If you move forward in our array, in our DP array, at index 5, my source is 5, right? So my source becomes 5 now, right? 5 calls for 2, 3, and 5, right? 5 can call for 2 as well as 3 as well as 5. Okay. When called for 2, 5 will land up at 3, right? It will go back to 5 minus 2, which is 3. 3 would say there is one possible way from me till 0, right? That is, if you attach 2 at the end of all of my permutations. So what we would have over here is 0.32, right? So this would give me one possible combination, possible permutation. Now, if I call for 3 from 5, it will land me up at 2, right? Then 2 would say, if I go back to 2, 2 would say I have one possible way. I have one possible way to reach 0, which is 0.2. So if I add 3 to 0.2, I would get another permutation. So I write this red, we would have 2, 3, right? Then 5 can call for 5, right? This would take it to 0. Okay, so 5 calls for 5. That means it goes back to 0. 0 says there is only one way from me till 0. That is, you don't do anything, right? You don't do anything. So you attach 5 over here. Before nothing, right? So we would have 3, 2, 2, 3, and 5 as possible permutations that can make a summation of 5. That means there is a total of 3. If you see over here, it's 1 plus 1 plus 1, which is 3. Right? I hope this is a bit clear now. If we move forward, right? Now, if we don't make the source and destination tree, if we just look at the DP now that we are on 6, what we can do is we can call for 2, 3, 5, and 6. So first of all, I would go to 2. That means 6 minus 2, which is 4. It would say there is only one way. So what are those ways? Those are 0.22, and I would add 2 behind it, right? So that's the one way, right? 1 plus. Now 6 would call for 3. 6 minus 3 would land it up on 3. 3 would say there is one way from me till 0, which is 0.3. So I would add my 3 behind the permutation, which is 0.3. Right? So I get 3, 3. That means another possible permutation that I get. Now I can also call for 5, right? So it goes to 5. It calls for 5. 6 minus 5 gets it to 1. 1 says there is 0 possible ways. So I would just go here and add 0, and I won't do anything as there is no possible way, right? Again, if we see over here, 6 can also call for 6. If 6 calls for 6, it will land us in 0th position, right? As soon as we get at 0th position, 0 would say one possible way, don't do anything. That means I will say, okay, if I don't do anything and I have 6 behind me, then this would be a possible permutation. That means plus 1, right? So if we see over here, we have a total of 3 permutations, right? We write this. So we have a total number of 3 permutations, right? Again, what we can do is move on to 7th position, which is our last position. From 7, again, we can call for 2, 3, 5, and 6, all of them, right? As 7 is greater than all of them. So 7 calls for 2, gets to 5. It says, okay, we have 3 over here, right? So the last one I would be drawing with black pen, right? So I call for 2, I get to 5, and 5 says that there are 3 possible permutations, right? Which are 3, 2, and if I add 2 behind it, it's 2, 3, and I add 2 behind it, it's 5, and I add 2 behind it. These 3, right? So it would be 3 plus. Then 7 can call for 3. So 7 goes for 3, gets to 4, and 4 says, okay, there is one possible permutations from me to 0, which is 2, 2. You can add 3 behind it and get to 7. So we have 2, 2, and 3 over here, right? We get 1. Okay. Now 7 calls for 5. So 7 minus 5 lands at 2, right? 2 says one way from me till 0, which is 0.2. You can add 5 behind it and get to 7. All right. So I get one possible way when I call for 5. What if I call for 6 now? If I call for 6, it will lend me to 7 minus 6, which is 1. Now 1 again says, sorry dude, no possible way from me till 0. That means you can't ever reach 0 if you use 6 from 7, right? So I won't be able to do anything, plus 0, right? So if we see what we have over here is 3 plus 1, 4, 4 plus 1, which is a total of 5, which is my answer. If we look over here, right? If we look over here, for the same test case, we had 5 as our answer. 2, 5, 2, 2, 3, 5, 2, 2, 3, 2, 3, 2, 2. Right? And if we look over here, these are the permutations that we have. Right? So this is our answer. So what we did was we took a particular position, a particular amount, and we traversed through all the coins. And for the coins that we could use at a particular amount, we used that and we generated all the possible permutations that we could. Right? Let's try to code this. Let's try to code this and see how we can work, right? So we can have a scanner, right? And we have n number, then we have n numbers, which are the elements, which are the coins, and then we have the amount. So we code this, we would need a scanner object. Right? Then the very first thing that we have to take is n, which are the number of coins. Then the second thing is the coins array. Right? We have to create a coins array of size n, of course. And then we have to take all of those coins as input. So we have coins of I equal into sc dot next int, and then what we need to do is take another input, which is our amount. So sc dot next int, right? Till here we have taken the input. Now what we have to do is the very first step that we had, which is assigning storage, right? What was our storage now? Our storage was an integer dp array of size amount plus 1. So quickly, if we write that, dp is equal to new int plus 1, right? Now what was our base case? Our base case was when we have a summation of 0, which is dp of 0, we don't have to do anything. The only way to pay is not pay anything. So dp of 0 was 1. This is our base case, right? Now we have to traverse and solve. How do we traverse? At every particular amount, at every particular position in the dp, we are trying all the possible ways in which we can generate that amount from all the coins, right? This helps us create permutations. So what we will do is the outer loop will go from 1 till the amount, right? As 0 is something that we have already handled, which is the base case, we run from 1 till amount. Okay. And the inner loop will be for coins, right? So we would pick each and every coin one by one. So j goes from 0 till n, j plus plus, right? And over here we can have coin equal to coins of j. So we have coins over here, right? So now what we have to check is if my coin that we have right now has a value which is either smaller than or equal to the current amount that I have. What is the current amount? Current amount is I, my index, right? So the index should be greater than or equal to the value of the coin. Then only I can make a call. And what does the call mean? Call just means that I would go back and I will add all the possible permutations that I had from the mediator, right? So dp of I or dp of I would be equal to dp of I minus coin, right? This would be plus equal to, because we are adding all of them, right? So after these for loops, we would have our answer in the last position of the DP array. The last position of the DP array is DP of amount. So we can directly print that. Right? This looks fine. Let's run this and see if it works or not. And it does. So let's submit for all the test cases. Right, so it submits. We are getting 10 out of 10. Now, if you go back, again, what we did was traversed, and for each and every amount, we tried all the possible ways in which we can accommodate all the coins, right? That helps us create the permutations 322, 232, 223, 5225, all of these, right? So again, what was the difference between this and coin change combinations? Coin change combinations, what we did was for a particular coin, we looked out for all the amounts that are possible using that particular coin, right? But in coin change permutations, we took a particular amount and we tried all the coins, right? This gave us rearrangements, right? So what we did, if you have seen the solution for coin change combinations, what we did was just replace the for loops. We just replaced the for loops and we got all the rearrangements. And this is why we got all the rearrangements. In coin change combinations, we prevent rearrangements from happening because we calculate all the amounts for a particular coin at a given point of time. So if I'm calculating all the amounts for 2, and after that I'm calculating all the amounts for 3, when I'm calculating for 3, the way I'm working, it prevents 2 from reappearing again. But in this case, as I'm working at a particular amount, I use all the coins, and then I'm working on another particular amount, I use again all the coins, I would get the coins back. That means I will get the rearrangements, right? Whereas the formula and the concept, both are similar, right? At last, talking about the time complexity. So we were able to solve this question using 2 for loops. The first one running from 0 to amount, 1 to amount, and the second one from 0 to n, which is O of n into amount. If more generalized, it's O n square. This is my time complexity. And for my space complexity, I had a DP array of integers of size amount plus 1. That means O of amount plus 1. Or more generalized, you can say O of n. Right? So O n square time complexity and O n space complexity. I hope you understood the solution. I hope you understood the difference between combinations and permutations, coin change, and I hope you were able to significantly tell the difference between rearrangements and how we prevented them from happening, right? So I will see you in the next video. Bye-bye.